Welcome, dear friend, to the Sleepy Scholar. In this video, we invite you to embark on a tranquil journey into the very heart of existence, exploring how quantum physics illuminates the fundamental nature of reality. Over the course of the next 2 hours, we will gently guide your imagination through the principles that govern the universe's tiniest inhabitants, from the mysterious duality of waves and particles to the spooky connections of entanglement and beyond. Each chapter has been carefully crafted not just to educate, but to help you unwind, allowing you to learn something truly fascinating while you gradually drift toward a peaceful slumber. So please find a comfortable position, let the tension leave your body, relax your mind, and let the quiet, beautiful strangeness of the quantum world carry you away into dreams. Chapter 1. What is quantum physics? Quantum physics stands as the branch of science dedicated to explaining the behavior of the absolute smallest components of our universe. It is the study that describes how atoms, electrons, photons, and a host of other subatomic particles interact, move, and sustain their existence. Unlike the realm of classical physics, which serves us perfectly well for understanding everyday objects like orbiting planets, speeding cars, or even the tumbling grains of sand on a beach, quantum physics applies to a domain hidden from the naked eye. It rules over the atomic and subatomic scales, a place where the familiar laws of the universe seem to dissolve, replaced by rules that are entirely unfamiliar and often counterintuitive. To truly grasp the significance of quantum physics, it is immensely helpful to journey back in time and understand the history of why such a theory became necessary in the first place. As we approach the dawn of the 20th century, the world of physics was viewed by many as a nearly complete masterpiece. Classical theories such as Isaac Newton's laws of motion, James Clerk Maxwell's elegant equations for electromagnetism, and the robust laws of thermodynamics had successfully explained almost every phenomenon observed in nature up to that point. There was a prevailing sense of confidence, a belief that all the fundamental questions of the cosmos had been answered, and that the work of future physicists would be merely to make minor measurements and refinements to the existing data. However, as scientists began to scrutinize certain phenomena with greater precision, cracks began to form in this classical framework. One of the first and most significant problems emerged from the study of something known as black body radiation. A black body is a theoretical, idealized object that absorbs all radiation falling upon it and emits energy purely based on its temperature. According to the established rules of classical physics, the energy emitted by such a body was predicted to increase infinitely as the wavelength of the radiation became shorter. This prediction led to a paradoxical and impossible result known as the ultraviolet catastrophe. The reality, however, was quite different. Experiments simply did not match this classical prediction. Instead of skyrocketing to infinity, the emitted energy peaked at a specific wavelength and then dropped off, a behavior that classical theory was completely at a loss to explain. It was in the year 1900 that the German physicist Max Planck stepped forward with a bold and revolutionary solution. He proposed that energy is not emitted in a continuous, unbroken flow, but rather in discrete, individual packets. Planck named these packets quanta. and they formed the bedrock of a radical new idea that energy could only exist in specific, defined amounts. To describe this relationship mathematically, Planck introduced a new fundamental number, which would come to be known as Planck's constant. His famous equation, E equals h times F, described energy as being directly proportional to frequency, with h representing this new constant. Although Planck himself initially viewed this concept as merely a mathematical trick to make the equations work, his idea actually laid the foundation for an entirely new understanding of energy, light, and matter. A few years later, Albert Einstein took Planck's concept even further while he was investigating a phenomenon called the photoelectric effect. This effect is observed when light strikes a metal surface and causes electrons to be ejected from it. Classical physics predicted that if you simply increase the brightness or intensity of the light, it should release more electrons with greater energy, regardless of the light's color or frequency. But once again, nature refused to cooperate with classical expectations. Experiments demonstrated that only light above a certain frequency, essentially a certain color, could cause electrons to be emitted, no matter how bright or intense the light source was. Einstein explained this puzzle by proposing that light itself is composed of particles, which we now call photons. He argued that each photon carries a specific, discrete amount of energy determined by its frequency. If a single photon did not possess enough energy to knock an electron loose, then no amount of brightness would make a difference. This explanation was a direct validation of Planck's quantum hypothesis, and it was this specific discovery that earned Einstein the Nobel Prize in 1921. The notion that light, which had long been understood as a wave, could also behave as a particle was deeply unsettling to the scientific community of the time. However, it soon became clear that this duality was not limited to light alone. In 1924, the French physicist Louis de Broglie made a daring suggestion. If light waves could act like particles, perhaps matter particles could exhibit wave-like properties. This idea, which was initially seen as highly speculative, was later confirmed by experiments demonstrating that electrons, previously thought to be solid little spheres, could form interference patterns. These patterns were behaviours that had previously been associated exclusively with waves, such as when water ripples overlap. This confirmation came when electrons were passed through a double-slit apparatus, proving that all particles could exhibit both wave and particle characteristics, depending on how they were observed. With these groundbreaking discoveries, a new branch of physics began to take shape, one that would require a complete rethinking of nature's laws. Throughout the 1920s, brilliant minds such as Werner Heisenberg, Erwin Schrödinger, and Paul Dirac developed the complex mathematical systems that would become known as quantum mechanics. Heisenberg's approach, known as matrix mechanics, focused on observable quantities and how they evolved over time. Schrödinger took a different path, introducing wave mechanics and the now famous wave function, a mathematical representation of a quantum system's possible states. Dirac later succeeded in combining quantum theory with Einstein's special relativity, even predicting the existence of antimatter. Despite appearing to follow different intellectual paths, these various approaches turned out to be mathematically equivalent, offering different perspectives to understand the same strange rules governing the quantum world. Together, they built the framework of modern quantum mechanics. At the very core of this framework lies a collection of principles that defy our everyday experiences and intuition. In the quantum world, certain physical properties are quantized, meaning they can only take on specific, discrete values. For example, the energy levels of an electron orbiting in an atom are not continuous like a ramp. They are distinct steps like a ladder. An electron must absorb or release a precise amount of energy to jump between these levels. This jumping behavior is completely unlike anything we see in the macroscopic world. Another key principle is the idea of superposition. In our classical understanding, a coin is either heads or tails. But in the quantum world, until we actually observe it, a system can exist in a blend of multiple states simultaneously. This isn't just a limitation of our knowledge, it is a fundamental property of the system itself. Only when we measure it does the system appear to choose a specific outcome. Even more surprising is the phenomenon of entanglement. When two particles become entangled, the state of one becomes directly and instantly related to the state of the other. No matter how far apart they are separated, even across the universe, measuring one instantly reveals information about the other. This strange link has been tested repeatedly in laboratories and has always agreed with the predictions of quantum mechanics. Another core idea is uncertainty. Werner Heisenberg formulated a principle showing that certain pairs of properties, like a particle's position and its momentum, cannot both be precisely known at the exact same time. The more accurately you measure one, the less precisely you can know the other. This is not due to flaws in our measurement tools, it is an intrinsic feature of quantum systems. To make predictions in quantum physics, scientists use wave functions, which are mathematical tools that describe the probability of finding a system in any given state. Unlike classical physics, which predicts definite deterministic outcomes, quantum physics deals in likelihoods. When we measure a system, we obtain one result, but before that moment, only probabilities exist. Many experiments have confirmed the principles of quantum mechanics with astounding precision. One of the most famous is the double-slit experiment with electrons. When electrons are fired at a barrier with two slits and no observation is made, they form an interference pattern, suggesting they are behaving like waves. But if we place detectors to see which slit each electron passes through, the interference pattern vanishes and the electrons behave like simple particles. This shift, based solely on observation, is one of quantum physics' most puzzling and compelling features. Other experiments, like those testing Bell's inequalities, have shown that entangled particles violate the predictions of classical physics, further confirming the accuracy of quantum theory. Quantum tunneling, another confirmed phenomenon, shows that particles can pass through barriers that should be impenetrable according to classical mechanics. This behavior plays a critical role in the fusion reactions that power our sun and is used in technologies such as tunnel diodes. Quantum physics isn't just theoretical, it is essential for much of our modern technology. Transistors, the fundamental building blocks of all computers and smartphones, rely on the quantum behavior of electrons in semiconductors. Lasers operate based on electrons moving between quantized energy levels. Magnetic resonance imaging, or MRI, uses nuclear quantum properties to form detailed images of the human body. Even future technologies like quantum computing aim to harness phenomena like superposition and entanglement to solve problems far beyond the reach of traditional machines. All of this is possible because quantum physics accurately describes how nature behaves at its most fundamental level. It departs from our classical intuitions but replaces them with a set of rules that are not only consistent and testable, but astonishingly precise. These rules may seem strange, but they are the foundation upon which much of our modern world is built. In summary, quantum physics is the study of how the universe operates at the smallest scales. It arose from the need to explain phenomena that classical theories could not, and it introduced concepts that challenge our common sense but have stood the test of time through experiment and application. Though abstract and often counterintuitive, quantum mechanics has proven to be one of the most successful and transformative frameworks in the history of science. Chapter 2: Wave-particle duality. Wave-particle duality stands as one of the most fundamental and surprisingly beautiful principles in all of quantum physics. It refers to the profound fact that all particles, including light and matter, can exhibit both wave-like and particle-like properties depending entirely on how they are observed. This concept reshaped our understanding of the physical world and marked a major turning point in the development of modern physics. The story begins with the mystery of light. For centuries, scientists engaged in a spirited debate over whether light was composed of waves or particles. In the 1600s, Isaac Newton championed the idea that light was made of particles, which he called corpuscles. Around the same time, the Dutch physicist Christian Huygens argued that light was a wave, behaving similarly to ripples spreading across a pond. These two competing theories coexisted for a long time, with experimental evidence seemingly supporting both at various points in history. However, in the 19th century, the wave theory began to gain significant ground. Experiments conducted by Thomas Young in 1801 showed that when light passes through two narrow slits and hits a screen behind them, it creates a pattern of alternating bright and dark bands. This is known as an interference pattern, and it is a characteristic signature of wave behavior. If light were simply a stream of particles like tiny bullets, one would expect to see two bright spots directly behind the slits, not an intricate spreading pattern of bands. The wave model explained this beautifully, and for much of the 19th century, light was widely accepted to be a wave. But the particle model of light returned with a surprising twist in the early 20th century. In 1905, Albert Einstein provided an explanation for the photoelectric effect, the phenomenon in which light striking a metal surface can eject electrons from it. Classical wave theory could not explain why light below a certain frequency, no matter how bright or intense, failed to knock any electrons loose. Einstein proposed that light comes in discrete packets or quanta, which are now called photons. Each photon carries energy proportional to its frequency. If a single photon's energy isn't high enough, it simply cannot dislodge an electron, regardless of how many photons bombard the surface. This observation could only be explained if light possessed particle-like properties. Suddenly, two conflicting behaviors, wave-like interference and particle-like quantization, both seem to be true. This was the first clear sign that the classical categories of wave and particle were no longer sufficient to describe reality. Then came the astonishing idea that wave-particle duality might apply not just to light, but to matter as well. In 1924, French physicist Louis de Broglie proposed that electrons, which were firmly believed to be solid particles, might also exhibit wave-like properties. He suggested that every particle with momentum has an associated wavelength, now referred to as the de Broglie wavelength. Though the idea was unconventional at the time, it had deep theoretical implications and opened the door to a unified view of matter and energy. In 1927, this hypothesis was tested experimentally by Clinton Davison and Lester Germer in the United States. They observed that a beam of electrons scattered off a crystal of nickel produced a diffraction pattern, just like X-rays or visible light would. This was conclusive proof that electrons could indeed behave as waves. Around the same time, similar experiments by George Thomson, the son of J.J. Thomson, who had discovered the electron as a particle, confirmed the same result. The dual nature of matter was no longer just a theory, it was an observable fact. This discovery was revolutionary. Electrons, previously thought to be point-like particles, could behave like waves under the right conditions. These were not metaphors or approximations. The wave behavior was real and measurable. The implications were profound. It meant that all matter has a dual character, and what we observe depends on how we choose to observe it. One of the most powerful demonstrations of wave-particle duality is the double-slit experiment. In this setup, a beam of particles, such as photons, electrons, or even larger molecules, is directed at a barrier containing two slits. Behind the barrier sits a detection screen. If only one slit is open, particles pass through and form a single band on the screen. However, if both slits are open and no observation is made regarding which slit each particle passes through, an interference pattern emerges indicating wave-like behavior. The particles interfere with themselves, creating regions of high and low probability. But here is the twist. If a detector is placed to observe specifically which slit each particle goes through, the interference pattern instantly disappears. The particles begin to form two distinct bands, behaving exactly as if they were little bullets. This shift in outcome, depending only on the presence or absence of measurement, is a defining characteristic of quantum mechanics. It challenges the idea that particles have definite paths or properties before we measure them. Instead, it suggests that the act of observation plays a fundamental role in determining the behavior of the system. The behavior of quantum objects is described mathematically by wave functions. These wave functions spread out over space and represent the probability distribution of finding a particle in a particular location. The wave function evolves according to Schrödinger's equation, a central formula in quantum mechanics. When no measurement is made, the particle's position is spread across many possibilities. When a measurement occurs, the wave function collapses and the particle appears in one specific location. This probabilistic nature of quantum systems is not due to experimental imperfections or a lack of knowledge on our part. It is inherent in the mathematics and the behavior of the system itself. Even with perfect information about the wave function, one cannot predict with certainty the exact outcome of a single experiment. Only the probabilities are known in advance. This dual nature applies not just to electrons or photons, but to all particles. In recent decades, scientists have demonstrated interference patterns using entire atoms and even large molecules composed of dozens of atoms. These results indicate that wave-particle duality is a general property of nature, not restricted to light or exceedingly small particles. The reason we don't see everyday objects waving like this is that the larger the object, the shorter its wavelength. From macroscopic objects like a baseball or a car, the wavelengths are so incredibly tiny that they become negligible for any practical purpose. Despite its abstract nature, wave-particle duality has practical consequences. It is essential to understanding the structure of atoms, the behavior of electrons in solids, and the mechanisms behind technologies like electron microscopes and semiconductor devices. In electron microscopes, the wave nature of electrons allows scientists to achieve resolutions far beyond those of traditional light microscopes, revealing structures at the nanometer scale. Wave-particle duality also lies at the heart of quantum field theory, the framework that combines quantum mechanics with special relativity. In this theory, particles are viewed as excitations or quanta of underlying fields that permeate all of space. These fields vibrate and interact, and the resulting phenomena are interpreted as particles. In this sense, particles are localized expressions of field waves, reinforcing the duality in a more modern form. Understanding wave-particle duality has forced physicists to abandon classical intuitions and accept a more complex but accurate description of the universe. Rather than asking whether something is a particle or a wave, quantum physics teaches us that those labels are limited and context-dependent. What matters is the system's behavior under specific conditions and how we choose to measure it. This principle does not indicate a flaw in our logic or experiments, but rather reveals a deeper layer of reality that becomes visible only at very small scales. Wave-particle duality isn't a contradiction. It is a broader understanding that nature doesn't fit neatly into classical categories. Instead, it follows its own rules, and those rules become visible when we ask the right questions in the right ways. Even though this behavior might seem foreign compared to the stability of the macroscopic world, it forms the foundation for all matter, energy, and interaction. Every atom in your body, every beam of light you have ever seen, and every material object around you owes its properties to this quantum duality. It is one of the most tested, confirmed, and powerful ideas in all of physics. By revealing that entities can act like both waves and particles, depending on how we observe them, wave-particle duality reshaped science. It opened new paths for inquiry and innovation and gave us tools to explore nature at its most fundamental level. In doing so, it continues to guide both theoretical research and practical technology, even a century after its discovery. Chapter 3: The Uncertainty Principle. The uncertainty principle is one of the most iconic and foundational elements of quantum physics. It fundamentally reshapes how we think about measurement, precision, and the very nature of physical reality at microscopic scales. First formulated by the German physicist Werner Heisenberg in 1927, the uncertainty principle reveals a strict limit on how precisely we can simultaneously know certain pairs of physical properties of a quantum system. It is crucial to understand that this is not just a technical limitation of our instruments, but a built-in feature of how nature operates at the smaller scales. At its core, the uncertainty principle tells us that there is an unavoidable trade-off in the precision with which we can measure two related quantities. The most commonly discussed example is the relationship between a particle's position and its momentum. Momentum is the product of mass and velocity. In classical mechanics, both position and momentum can be measured with infinite precision. If we simply use sufficiently accurate instruments, we can know exactly where a car is and exactly how fast it is moving. But quantum mechanics introduces a different framework, one where particles are described not by precise locations and speeds, but by wave functions, mathematical descriptions that represent probabilities. The wave function for a quantum particle, such as an electron, spreads out in space. It tells us where the particle is likely to be found if we perform a measurement, but it does not give a definite location until that measurement is actually made. The wider the wave function spreads in space, the more uncertain the position of the particle becomes. Conversely, if the wave function is narrow and concentrated in space, indicating a well-known position, then its spread in momentum becomes larger. This inverse relationship between the spread in position and the spread in momentum is exactly what the uncertainty principle describes. The formal expression of Heisenberg's principle is often written as an inequality. The product of the uncertainties in position and momentum must be greater than or equal to a small constant. That constant is Planck's reduced constant divided by 2 pi. Mathematically, it implies that the more precisely we try to determine a particle's position, the less precisely we can know its momentum, and vice versa. This relationship is not due to flaws in our equipment. Even with perfect detectors and zero experimental error, the uncertainty principle still applies. It is a direct consequence of the wave-like nature of particles. To understand why, consider a basic wave. A single frequency wave extends infinitely in space. It has a very well-defined wavelength and therefore a very well-defined momentum. But because it is spread out evenly across the universe, it has no particular location. It is completely delocalized. On the other hand, to localize a wave in space, to create a wave packet that has a specific position, you must combine many different frequencies. The result is a superposition of waves with slightly different momenta, leading to a wave packet that is localized in space but uncertain in momentum. This trade-off is not limited to position and momentum. The uncertainty principle applies to other pairs of quantities as well, such as energy and time, or angular momentum and orientation. In each case, there is a fundamental limit to how precisely both properties can be known at the same time. These relationships are all rooted in the mathematical structure of quantum mechanics, particularly in the way operators, mathematical tools that represent observable quantities, do not commute when applied in different orders. One of the most important consequences of the uncertainty principle is that it undermines the classical idea of determinism. In Newtonian physics, if we know the position and momentum of every particle in a system, we can, in theory, predict the future state of the system with perfect accuracy. But in quantum mechanics, such complete knowledge is impossible. We can only speak in terms of probabilities and likelihoods, not certainties. The future is not fixed, but governed by probability distributions that emerge from the wave function. This principle also has profound implications for our understanding of what it means to observe or measure something. In classical science, measurement is passive. We look at a system and our observation reveals properties that were already there. In quantum mechanics, however, measurement is an active process that alters the state of the system. The uncertainty principle ensures that the more we try to pin down one property, the more we disturb its complementary property. One famous thought experiment that illustrates this is Heisenberg's microscope. Imagine trying to observe an electron using a microscope that uses light. To get a clear image, we might try to use high-energy photons with short wavelengths. These would allow us to resolve small details and determine the electron's position more precisely. However, the high-energy photon would also transfer a large amount of momentum to the electron upon interaction, wildly disturbing its velocity. If, instead, we use lower energy photons to avoid disturbing the electron's momentum, the long wavelength of the light blurs our image and makes the position less precise. This dilemma exemplifies the unavoidable trade-off between knowing position and knowing momentum. In practical terms, the uncertainty principle sets hard limits on what we can know about systems like atoms, molecules, and subatomic particles. For example, it explains why electrons in atoms do not simply spiral into the nucleus. If an electron were confined to an extremely small region near the nucleus, its position would be very well defined. However, according to the uncertainty principle, its momentum, and thus its kinetic energy, would have to be extremely large, making such a state unstable. Instead, electrons exist in regions of space called orbitals, which represent the probability distributions of where an electron might be found. These orbitals are stable precisely because of the delicate balance enforced by the uncertainty principle. The uncertainty principle is also essential to understanding the concept of zero-point energy, the idea that quantum systems never come completely to rest, even at absolute zero temperature. A quantum harmonic oscillator, such as a vibrating atom in a crystal lattice, retains a minimum amount of energy due to the constraints of the uncertainty principle. If it had zero energy, its position and momentum would both be exactly known, both zero, which the principle forbids. This residual energy is an unavoidable consequence of the quantum rules. In the realm of particle physics, the uncertainty principle provides insight into the fleeting nature of certain particles and phenomena. For instance, virtual particles, which briefly pop in and out of existence in quantum field theory, are permitted to violate conservation of energy for very short periods of time, a phenomenon allowed by the time-energy form of the uncertainty principle. These virtual particles contribute to observable effects such as the Lamb shift in atomic energy levels and the Casimir effect between closely spaced plates. Although these implications may seem abstract, the uncertainty principle has very real and measurable consequences. Its predictions have been confirmed in countless experiments across decades of research. It plays a central role in quantum optics, where the manipulation of light at the quantum level requires precise control over complementary variables such as phase and amplitude. It also affects precision metrology, the science of making extremely accurate measurements by defining the ultimate sensitivity limits for instruments like atomic clocks and gravitational wave detectors. Understanding the uncertainty principle requires a shift in perspective. In the classical world, it makes sense to imagine that particles have exact positions and velocities at all times, even if we don't know them. but quantum physics forces us to accept a new kind of knowledge, one that is inherently probabilistic and based on what can and cannot be known simultaneously. This does not mean that the quantum world is chaotic or ill-defined. On the contrary, it follows strict rules and yields precise statistical predictions. But those predictions concern distributions and likelihoods, not fixed outcomes. The uncertainty principle is not a failure of measurement. It is not a technological limitation. It is a fundamental characteristic of how nature works. It is built into the mathematics of quantum theory and supported by a century of experimental validation. Rather than thinking of it as an obstacle, physicists have embraced it as a guide, a principle that shapes everything from the stability of atoms to the behavior of black holes. Even though the principle applies at scales far smaller than everyday life, it underlies the behavior of all matter and energy. It explains why the atomic world is structured the way it is, why electrons occupy specific energy levels, why chemical bonds form, and why the universe is not frozen into deterministic predictability. It introduces a kind of built-in fuzziness to reality, a reminder that even the most fundamental quantities in the universe come with a degree of inherent variability. In the vast landscape of physics, the uncertainty principle stands as a quiet but powerful reminder that knowledge itself has limits, and within those limits new insights arise, not from the ability to know everything, but from understanding the boundaries of what can be known. Chapter 4. Quantum superposition. Quantum superposition stands as one of the most essential yet undeniably puzzling concepts within the vast landscape of quantum physics. It refers to the profound idea that a quantum system, whether it be an electron, a photon, or an atom, can exist in multiple possible states at the exact same moment. It is only through the act of observation that the system settles into a single, definite outcome. This principle is not merely a theoretical curiosity scribbled on a chalkboard. It has been observed in countless experiments and lies at the very heart of how the microscopic world operates. Yet, it defies our common sense and our everyday understanding of reality, where objects appear to be in one state or another, never both at once. In the world of classical physics, the world of tables, chairs, and coffee cups, an object can be in only one state at a given time. A ball is either on the left side of a table or the right. A light switch is either flipped on or flipped off. This is how we are accustomed to thinking about the world in terms of clear, definite, and mutually exclusive conditions. But in the quantum realm, the behavior of particles is governed by wave functions, those mathematical descriptions that map out the probabilities of different outcomes. Until a measurement is made, the system is not locked into one of those outcomes. It is, quite literally, in all of them at once, held in a delicate state of superposition. To truly understand the beauty of superposition, it helps to consider how particles behave as waves. In quantum mechanics, particles are associated with wave functions that are not physical waves like those in the ocean or sound waves in the air, but abstract mathematical functions describing likelihood. When a particle has the potential to be in more than one state, its total wave function is formed by adding together the wave functions of all those individual states. This addition is not a messy, random mixing. It is a coherent sum, where the individual components interfere with each other, much like overlapping ripples on the surface of a quiet pond. The result of this mathematical addition is a new wave function that reflects the superposition of all possible states the particle could occupy. For example, imagine an electron that could be in location A or location B. Its wave function might include both locations simultaneously. Before any observation is made, the electron is not just possibly in A or possibly in B. It is truly in both, described by a wave function that encompasses both possibilities at once. The probabilities of finding the particle in either location only become real facts when a measurement is made, causing the wave function to collapse into a single outcome. One of the most famous illustrations of this concept is the thought experiment known as Schrödinger's cat, devised by the Austrian physicist Erwin Schrödinger in 1935. This scenario describes a cat placed in a sealed box with a mechanism that has a 50% chance of releasing a poison, dependent entirely on the random decay of a single radioactive atom. According to quantum theory, until the box is opened and the system is observed, the atom exists in a superposition of decayed and undecayed states. Consequently, the cat is considered to be both alive and dead. Schrödinger did not mean this, literally in the sense of a zombie cat. His point was to highlight the sheer strangeness of applying quantum rules to macroscopic objects. In practice, observing quantum superposition at large scales is incredibly difficult because larger systems quickly interact with their environments. This interaction leads to a process known as decoherence, where the system loses its quantum coherence and begins to behave like a normal classical object. But at small scales, such as with individual atoms, electrons, or photons, superposition is not only real, it is measurable. Experiments have repeatedly confirmed the existence of superposition. In one example, scientists send individual electrons through a pair of slits in a barrier. If no measurement is made to determine which slit the electron passes through, the electron behaves as though it travels through both slits simultaneously, creating an interference pattern on a screen. This pattern is the direct result of the electron's wave function being in a superposition of went through slit A and went through slit B. Only when detectors are placed to monitor the path does the interference vanish, and the electron behaves like a classical particle that chose one path or the other. Superposition is not limited to position. Quantum systems can be in superpositions of other properties, such as spin, polarization, or energy levels. For instance, the spin of an electron, a quantum version of angular momentum, can point in different directions. Until it is measured, the spin can be in a superposition of up and down. Once measured, the spin adopts a definite value. But before that moment, the particle is in a genuine quantum mixture of both possibilities. This principle is also used in experiments with photons, where polarization, the orientation of the light's electric field, can exist in a superposition of horizontal and vertical states. These behaviors are not mere quirks of theory, they are experimentally verified and mathematically predictable. In fact, the emerging field of quantum computing relies heavily on the principle of superposition. Unlike classical computers, which use bits that can be in one of two states, 0 or 1, quantum computers use quantum bits or qubits. These qubits can exist in superpositions of both 0 and 1 at the same time. This allows quantum computers to perform certain calculations much more efficiently than classical machines by processing multiple possibilities in parallel. However, maintaining superposition in qubits is a major technical challenge, as they are extremely sensitive to noise and environmental interactions that cause decoherence. The phenomenon of superposition also plays a critical role in quantum chemistry and atomic physics. Electrons in atoms are described by wave functions that form standing wave patterns around the nucleus. These standing waves represent superpositions of possible positions and energies. The shapes and interactions of these wave functions determine how atoms bond with each other to form the molecules that make up our world. In chemical reactions, the transition states between reactants and products often involve complex superpositions of different bonding arrangements. Superposition is not simply a curiosity. It is at the very heart of why quantum systems behave differently from classical ones. It introduces the profound idea that particles do not have definite properties until those properties are observed. This leads to deep philosophical questions about the nature of measurement, the role of observers, and the completeness of quantum theory. While these questions have sparked debate and various interpretations of quantum mechanics, the physical reality of superposition has never been in doubt. Physicists have also explored superposition using increasingly large systems. In recent years, researchers have managed to place small molecules consisting of dozens or even hundreds of atoms into superposition states. These experiments push the boundaries of how large a system can be while still exhibiting quantum behavior. Each new result provides stronger evidence that superposition is not strictly limited to the microscopic world, although maintaining coherence becomes exponentially harder as the system grows in size. Despite its strangeness, the mathematics of superposition is precise and reliable. The wave function that describes a quantum system evolves deterministically according to Schrödinger's equation until a measurement is made. This evolution preserves the superposed states and allows interference patterns to emerge. The predictive power of this mathematics has been confirmed across countless experiments and underlies much of modern quantum theory. Understanding superposition requires letting go of the comfortable notion that physical systems must always be in definite observable states. In the quantum world, potentialities coexist until the act of measurement reduces them to actualities. It is not that we simply don't know what state the system is in. Rather, the system truly exists in all its allowed states at once, each with a certain amplitude and phase that affect how it combines with others. The implications of this idea are vast, suggesting a level of indeterminacy in nature that is not due to ignorance or chaos, but is part of the fabric of reality itself. At the same time, superposition offers powerful tools for technology and scientific understanding. It enables precision control in fields like quantum optics and quantum information, and it plays a central role in the structure and behavior of atoms, molecules, and materials. The principle of superposition has been with quantum mechanics since its inception, and continues to be one of the most fascinating and experimentally confirmed aspects of the theory. It shows that the quantum world is richer and more complex than the classical one we see every day. In that richness lies both mystery and possibility, a framework that not only explains how particles behave, but also offers the foundation for some of the most advanced and promising technologies of the future. Chapter 5: Quantum Entanglement. Quantum entanglement is arguably one of the most intriguing, romantic, and experimentally confirmed phenomena in modern physics. It describes a condition in which two or more quantum particles become linked in such a profound way that the state of one particle cannot be described independently of the state of the other, no matter how far apart they are. This connection persists even when the entangled particles are separated by vast distances across a room, a continent, or even a galaxy. What happens to one immediately affects the other, not through any signal or force that travels between them, but as a consequence of the mathematics governing their shared quantum state. The concept of entanglement emerges naturally from the principles of quantum mechanics, particularly the idea of superposition. When two quantum systems interact and then separate, their wave functions can become entangled, meaning that their probabilities are no longer independent. Instead, they are described by a single, combined wave function that encodes correlations between the particles. These correlations remain even when the particles are no longer in physical contact. To grasp how entanglement works, it helps to consider a simple example involving particle spin. Spin is a fundamental quantum property akin to angular momentum. For electrons, spin can take one of two values, up or down. If two electrons interact in such a way that they must have opposite spins, their total spin state becomes entangled. This means that if one is measured and found to be spin up, the other will be instantly found to be spin down, and vice versa. But here is the catch. Until a measurement is made, neither electron has a definite spin. Instead, they both exist in a superposition of both possibilities, and the outcomes are strictly correlated. This entangled state does not depend on the distance between the particles. If one electron is sent to one side of the universe and the other to the opposite side, measuring the spin of one still determines the spin of the other instantly. This feature baffled even the founders of quantum theory. In 1935, Albert Einstein, along with Boris Podolsky and Nathan Rosen, published a paper arguing that such behavior implied that quantum mechanics was incomplete. They suggested that there must be hidden variables, unknown factors that predetermine the outcome of each measurement. Einstein famously referred to entanglement as spooky action at a distance, expressing his deep discomfort with the idea that one particle could instantaneously influence another without any physical connection. This led to the formulation of what became known as the EPR paradox, named after the authors of the paper. The paradox pointed out that if quantum mechanics were correct, it allowed for non-local effects, influences that seemingly travelled faster than light, appearing to violate the principle of causality. For decades, this question remained unresolved. Could there be hidden variables underlying quantum behaviour, or was the theory truly non-local in the way it appeared to be? In the 1960s, the physicist John Bell devised a brilliant way to test these competing ideas. He developed what are now called Bell inequalities, mathematical relationships that would be satisfied if hidden variables governed the outcomes of measurements. But if entanglement behaved as quantum mechanics predicted, then the inequalities would be violated. In the 1970s and 1980s, Experimentalists such as Alain Aspect and his team in France conducted rigorous tests using entangled photons and polarization filters. The results consistently violated Bell's inequalities, confirming that the correlations observed in entanglement could not be explained by local hidden variables. These experiments have since been repeated many times with increasing precision, using photons, electrons, ions, and other quantum systems. The conclusion is now clear. Quantum entanglement is a real, measurable, and well-understood feature of nature. It does not involve faster-than-light communication or any transfer of information in the traditional sense. What it demonstrates is that the properties of entangled particles are not independent. They are part of a single, unified system, regardless of spatial separation. The act of measuring one particle doesn't send a message to the other. Rather, it reveals a relationship that was already built into their joint wave function from the start. Entanglement challenges our intuitions about separateness and independence. In classical physics, objects have their own properties regardless of what happens to other objects. But in quantum mechanics, the state of a system can be fundamentally relational. Two particles that were once entangled remain connected, not through a physical tether, but through the mathematical structure of their wave function. This interconnectedness has practical implications beyond foundational philosophy. Entanglement is central to the development of emerging technologies in quantum information science. One of the most promising applications is quantum communication, specifically quantum key distribution, or QKD. In QKD, two parties can share a secret encryption key by exchanging entangled particles. Because the correlations between the entangled particles are perfect and cannot be intercepted without disturbing the system, any attempt to eavesdrop becomes immediately detectable. This property offers the potential for unbreakable encryption. Another application is quantum teleportation, which sounds like science fiction but is firmly grounded in experimental physics. Quantum teleportation does not involve transporting matter from one place to another like in the movies. Instead, it refers to the transfer of quantum states between distant particles using entanglement. By entangling two particles and performing a specific measurement on one of them in combination with another particle whose state is to be teleported, it is possible to transfer the state of that third particle onto the remote entangled partner. This process requires both quantum entanglement and classical communication, and it has been demonstrated many times in laboratories. Entanglement is also essential in the operation of quantum computers. In classical computing, bits are independent. Each bit can be either 0 or 1. In a quantum computer, however, qubits can be entangled with one another, allowing for complex correlations and parallelism that would be impossible with classical bits. This entanglement enables quantum algorithms to perform certain computations far more efficiently than their classical counterparts, offering the potential for breakthroughs in fields like cryptography, optimization, and materials science. On a more fundamental level, entanglement plays a role in our understanding of physical systems across many areas of physics. In quantum chemistry, entangled electrons determine the structure and stability of molecules. In condensed matter physics, entanglement underlies phenomena such as superconductivity and quantum phase transitions. In high-energy physics, entanglement is being explored in theories of black holes and the fabric of space-time itself. Some proposals even suggest that space-time geometry may emerge from patterns of entanglement in underlying quantum fields. While entanglement is a striking phenomenon, it does not allow for faster-than-light communication or violate the laws of relativity. Although the measurement of one particle's state instantly correlates with the state of its entangled partner, the outcomes are still random. This randomness ensures that no usable information can be transmitted faster than light. In other words, while the correlation is instantaneous, it cannot be used to send a message or cause an effect that breaks causality. This subtle but crucial distinction keeps quantum mechanics consistent with the principles of special relativity. The experimental confirmation of entanglement has been one of the great triumphs of modern physics. In recent years, researchers have entangled particles over distances of hundreds of kilometers, including between ground stations and satellites in orbit. These results not only support the theoretical foundations of quantum mechanics, but also open the door to global-scale quantum networks. The dream of a quantum internet, a network of entangled systems enabling ultra-secure communication and distributed quantum computing, is already under development. The fact that particles can remain entangled over such long distances without any classical connection or force between them speaks to the deeply non-local character of quantum mechanics. It shows that our classical intuitions about space, time, and separability are not fundamental features of the world, but approximations that break down at the quantum level. In this framework, information is not confined to single locations, but is spread out over entangled systems, forming correlations that defy classical logic but obey precise mathematical rules. Despite the counterintuitive nature of entanglement, it is now a well-understood part of the quantum world. Its predictions match experimental data with extraordinary accuracy, and its effects can be manipulated, harnessed, and controlled in the lab. What was once seen as a philosophical oddity has become a cornerstone of quantum technologies and a gateway to understanding the deeper structure of reality. As with many quantum phenomena, entanglement reminds us that our perceptions of how the world should behave are shaped by the macroscopic world we inhabit. But at the quantum level, the universe obeys rules that are richer, subtler, and more interconnected than our everyday experiences would suggest. By studying and applying those rules, we not only deepen our knowledge of the universe, but also develop new tools that may shape the future of science and technology. Chapter 6: The Observer Effect. The observer effect in quantum physics refers to the peculiar and often misunderstood phenomenon in which the act of measuring or observing a quantum system directly influences the system's behavior. Unlike classical physics, where measurements reveal pre-existing values without altering the system, quantum mechanics presents a reality where observation itself plays an active role. This concept is not merely philosophical, it is backed by mathematical formalism and repeated experimental confirmation, making it one of the central and most intriguing features of the quantum world. To understand the observer effect, it is important to begin with how quantum systems are described. In quantum mechanics, a system is represented by a wave function, a mathematical function that encapsulates all the possible states the system can occupy. This wave function doesn't assign exact values to physical properties like position or momentum. Instead, it provides the probability of finding the system in various states, For example, a particle's position isn't a fixed coordinate, but a range of possibilities, each with a certain likelihood. As long as the system remains unobserved, the wave function evolves smoothly and deterministically over time according to Schrödinger's equation. This evolution keeps all possible outcomes in a delicate balance, forming what is known as a quantum superposition. But when a measurement is made, when an observer tries to determine a specific property like the position of an electron, this smooth evolution is interrupted. The wave function appears to collapse into a single definite state corresponding to the measurement outcome. This collapse is not described by Schrödinger's equation itself, rather it is introduced as a postulate of quantum mechanics. Before measurement, the particle exists in a superposition of states. After measurement, it has a definite value. The transition from the superposition to the single state occurs at the moment of observation, and the outcome is probabilistic, governed by the square of the wave function's amplitude for each possible result. A classic demonstration of this effect is the double-slit experiment. When particles such as electrons or photons are sent toward a barrier with two slits, and no attempt is made to detect which slit they go through, they form an interference pattern on the screen behind the slits. This pattern is typical of waves, indicating that each particle somehow goes through both slits simultaneously in a superposition of paths. However, if a detector is placed at the slits to determine which slit each particle passes through, the interference pattern disappears. Instead, the particles behave like classical particles, forming two distinct bands behind the slits. The very act of observing which path the particle took changes the result. It is not that the detector disturbs the particle physically, though that can happen too. It is that the possibility of acquiring which path information destroys the interference pattern. This sensitivity to measurement suggests that observation is more than a passive process in quantum physics. It fundamentally alters the set of possibilities that the system can exhibit. In classical physics, you can observe a system without changing its state. Watching a planet orbit, for instance, has no effect on its motion. But in the quantum world, measurement and system are deeply intertwined. One important clarification is that the term observer in quantum mechanics does not necessarily refer to a conscious human being. In this context, an observer is any physical interaction that extracts information from the system. It could be a measuring device, a photon reflecting off a surface, or a particle detector. What matters is that a quantum system becomes entangled with its environment in a way that forces it into one of its possible states, thus collapsing the superposition. This transition from quantum indeterminacy to definite outcomes is sometimes called the measurement problem, and it has been the subject of extensive interpretation. The Copenhagen interpretation, which remains one of the most commonly taught frameworks, accepts the collapse of the wave function as a fundamental aspect of quantum theory. According to this view, the act of measurement causes the wave function to reduce to a single outcome, and there is no need to ask what the system was doing before observation. It simply had no definite properties. Other interpretations attempt to explain the observer effect in different ways. The many worlds interpretation, for example, denies that wave function collapse ever occurs. Instead, it proposes that all possible outcomes of a measurement actually happen, each in a separate branch of a continually splitting universe. In this view, measurement doesn't collapse possibilities. It reveals which branch you are on. While this removes the need for collapse, it introduces the idea of a vast multiverse where every possibility is realized. Still, other interpretations, such as decoherence theory, attempt to explain the appearance of collapse through the interaction of a quantum system with its environment. According to decoherence, the system's coherence, its ability to exist in a superposition, is rapidly lost as it becomes entangled with the surrounding environment. This process makes interference effects disappear and gives the appearance of classical outcomes, even though the wave function continues to evolve. Despite these differing viewpoints, the experimental fact remains that measuring a quantum system changes it. This is not limited to which path, decisions in the double-slit experiment. It applies across a wide range of quantum systems. For instance, in quantum optics, the detection of a single photon collapses the light field into a different state. In atomic physics, measuring the energy level of an atom alters the distribution of electrons. In quantum computing, reading the value of a qubit collapses its superposition into a single binary state. This effect is not just a curiosity. It has real consequences for how experiments are designed and interpreted. Quantum cryptography, for example, relies on the fact that any attempt to measure a quantum key in transit will alter it, revealing the presence of an eavesdropper. In quantum computing, algorithms are carefully structured so that useful outcomes emerge only after a final measurement step. Until that point, the quantum system evolves in a superposition of computational pathways. It is also important to note that not all quantum systems undergo collapse in the same way. In weak measurements, for instance, only partial information is extracted from the system, allowing some coherence to remain. These measurements can reveal certain properties of a system without fully collapsing its state, offering a middle ground between pure quantum superposition and classical certainty. Such techniques are increasingly used in experimental quantum physics and quantum information processing. The observer effect also brings subtlety to the idea of reality in quantum physics. If a system doesn't have definite properties until measured, then what can we say about its state before observation? Are we to assume that reality itself is undefined until it is probed? Some physicists embrace this view, accepting that quantum properties are relational and only acquire meaning in the context of an interaction or observation. Others prefer to treat the wave function as a tool for prediction rather than a direct description of reality. In this view, quantum mechanics doesn't tell us what the world is, only what we can expect to observe. This pragmatic approach works well for calculations and experiments, but it leaves open deeper questions about the nature of existence at the quantum level. What is clear is that the observer effect places measurement at the heart of quantum physics. It is not merely a step at the end of an experiment, it is a defining act that brings quantum possibilities into classical reality. Without measurement, the wave function continues to evolve, existing in a cloud of probabilities. With measurement, a single outcome emerges, consistent with the statistical rules of quantum theory. This transformation is governed by precise mathematical laws and produces highly accurate predictions. Despite its counterintuitive nature, quantum theory has never failed a test and continues to match experiment after experiment with extraordinary precision. The observer effect, once a philosophical oddity, is now part of the operational framework of quantum science. Ultimately, the observer effect reminds us that at the quantum level, knowledge and interaction are deeply connected. You cannot observe without participating. You cannot measure without influencing. This is not a flaw of the theory, it is one of its defining strengths, a reflection of the fact that at the smallest scales, the boundaries between system, instrument, and observer are blurred in ways that classical physics never imagined. Protons inside the Sun's core actually do not possess enough kinetic energy to overcome their mutual electrostatic repulsion. According to classical physics, they should bounce off one another, never getting close enough to fuse. If the universe followed only classical rules, the sun would not shine, and life as we know it would never have begun. However, quantum tunneling bridges this gap. It allows protons to occasionally tunnel through the repulsive energy barrier that separates them, enabling nuclear fusion to take place. This process releases the life-giving warmth and light that bathes our solar system. In a very real sense, the light touching your face on a sunny day is a direct gift from the phenomenon of quantum tunneling. Another profound example of this phenomenon is found in radioactive decay, specifically alpha decay. An alpha particle consists of 2 protons and 2 neutrons, essentially a helium nucleus. Inside heavy, unstable atomic nuclei like uranium, these alpha particles are trapped in a potential energy well created by the strong nuclear force. Classically, they should remain confined there forever, unable to escape the strong pull of the nucleus. But quantum mechanics allows these alpha particles to borrow energy, tunnel through the potential barrier, and escape, resulting in radioactive decay. The rate at which this happens can be calculated using tunneling probabilities, and these calculations match experimental observations with astonishing accuracy. Tunneling also plays an indispensable role in the electronics that define our modern age. In tunnel diodes, for example, electrons tunnel through a narrow region of insulating material between 2 conductors. This effect allows the diode to operate at incredible speeds and enables unique electrical properties used in high-frequency oscillators and amplifiers. Furthermore, consider the flash memory used in your smartphone, USB drives, and solid-state hard drives. This technology relies on electrons tunneling through thin insulating layers to get trapped in floating gates, effectively storing your data. Every time you save a photo or a document, you are harnessing the power of quantum tunneling. As we look even deeper, we find that tunneling becomes increasingly critical at the nanoscale. In the tiny transistors that make up modern computer chips, components are shrinking to the size of just a few nanometers. At these scales, electrons can tunnel between regions that are supposed to be electrically isolated, creating leakage currents that challenge engineers. This reminds us that quantum effects are not just theoretical puzzles, they are practical engineering constraints that must be managed to build the future of technology. There is even evidence that tunneling plays a role in the chemistry of life itself. In the complex dance of biological enzymes, the proteins that speed up chemical reactions in our bodies, research suggests that hydrogen atoms may tunnel between molecules. This quantum shortcut allows vital metabolic reactions to occur much faster than they would by classical means alone, hinting that the machinery of life may be running on quantum oil. Quantum tunneling also invites us to question the nature of time. When a particle tunnels through a barrier, it appears on the other side without having traversed the space in between in the traditional sense. The time it takes for a particle to tunnel has been a subject of intense debate among physicists. Some interpretations suggest the process is instantaneous, while others calculate a finite, albeit incredibly brief, duration. Regardless of the answer, tunneling shows us that at the quantum scale, the universe is a place where walls are not solid and the impossible becomes merely improbable. Chapter 8. The role of probability in quantum mechanics. Probability lies at the very beating heart of quantum mechanics. Unlike the comfortable predictability of classical physics, which deals in certainty and precise cause and effect, quantum mechanics operates on a fundamentally probabilistic framework. It does not allow us to determine the exact outcome of a single measurement in advance. Instead, it offers us the probability, the likelihood of each possible result, even if we possess every scrap of information about the system's current state. This reliance on probability is not due to ignorance, nor is it a result of clumsy instruments. It is built into the very laws that govern the quantum world. In the classical view of the universe, often compared to a giant clockwork mechanism, the behavior of every object could theoretically be predicted. If you knew the position and velocity of every particle in the universe, Isaac Newton's laws would allow you to calculate the future with perfect accuracy. This concept, known as determinism, suggested a world where the future was already written, merely waiting to unfold. But quantum mechanics shattered this view. It introduced a reality where the future is not fixed, but is rather a branching tree of probabilities. The central tool for navigating this probabilistic world is the wave function. This mathematical entity contains all the information about a quantum system. However, it does not tell you the electron is here. Instead, it provides a map of potentialities. To find the probability of an electron being in a certain spot, physicists take the amplitude of the wave function at that point and square it. This rule, known as the Born rule, transforms the abstract mathematics of waves into the concrete probabilities of the physical world. This means that an electron in an atom does not have a definite position until it is measured. It exists in a cloud of probability, a maybe, that is spread out across space. The wave function tells us where the electron is likely to be found and where it is unlikely to be found, but it never gives us a guarantee. This is a radical departure from our everyday experience, where your car keys are definitely either on the table or they are not. One of the most beautiful illustrations of quantum probability is the double-slit experiment. When we fire individual particles at the screen, each one lands in a seemingly random spot. We cannot predict where the next electron will hit. However, as we continue to fire thousands of particles, a pattern begins to emerge from the chaos. The accumulation of these random individual impacts forms a precise interference pattern, perfectly predicted by the probabilities of the wave function. This demonstrates that while individual quantum events are unpredictable, the statistical behavior of the whole is governed by strict, elegant laws. In the quantum world, probability governs every measurable quantity, not just position, but momentum, energy, spin, and polarization. For every property we wish to measure, quantum mechanics defines a set of possible outcomes and assigns a probability to each. These probabilities are not arbitrary, they emerge from the complex interaction of the system's wave function. Furthermore, the Heisenberg uncertainty principle guarantees that we can never escape this probabilistic nature. If we try to squeeze the probability of a particle's position into a sharp peak, knowing exactly where it is, the probability distribution of its momentum spreads out, becoming completely uncertain. Perhaps the most striking feature of quantum probability is that these probabilities can interfere with one another. Unlike classical probabilities, which simply add up, like the chances of rolling a die, quantum probability amplitudes act like waves. They can combine constructively to increase the likelihood of an event, or destructively to cancel it out completely. This interference is what allows quantum computers to solve problems. They manipulate these probability amplitudes to magnify the correct answer and cancel out the wrong ones. The randomness inherent in quantum mechanics is fundamentally different from the randomness of a coin toss. When you flip a coin, the outcome appears random only because you don't know the exact force of your thumb, the air resistance, or the friction of the table. If you knew all those variables, the coin toss would be predictable. In quantum mechanics, however, there are no hidden variables that determine the outcome. The unpredictability is intrinsic to nature itself. Even with godlike knowledge of the system, the specific outcome of a measurement remains a roll of the cosmic dice. This shift from certainty to probability has profound philosophical implications. It suggests that at its most fundamental level, reality is not fixed until it is observed. The universe is a sea of possibilities, constantly fluctuating until an interaction forces a choice. Despite this underlying randomness, the theory is incredibly successful. Technologies like lasers, MRI scanners, and atomic clocks all operate based on these probabilistic principles. The law of large numbers ensures that while single atoms are unpredictable, the billions of atoms in a computer chip behave reliably. By embracing probability as a fundamental part of physical law, quantum mechanics provides a deeper, more nuanced understanding of nature. It teaches us that the universe is not a rigid machine grinding inevitably forward, but a dynamic, vibrant system where potential and actuality dance together. Chapter 9: How Quantum Physics Changed Our View of Reality. Quantum physics has done more than just provide us with new equations. It has fundamentally revolutionized our philosophical understanding of the natural world. Before the dawn of the 20th century, science was grounded in the comforting principles of classical physics, a framework that described a universe of solid objects, definite locations, and predictable causes. In that old world, reality was objective and independent of us. A tree falling in a forest made a sound whether or not anyone was there to hear it. The arrival of quantum mechanics disrupted this worldview entirely. It replaced the clockwork universe with a reality that emphasizes uncertainty, probability, and the fundamental limits of what can be known. At the core of this shift is the realization that the building blocks of matter do not behave like tiny, solid marbles. Instead, entities like electrons and photons behave more like ghostly entities that are neither fully particle nor fully wave, but something more complex that transcends our ordinary language. Quantum mechanics challenges the very idea of existence as we know it. In the classical view, an object has properties, speed, color, weight, regardless of whether we are looking at it. In the quantum view, properties are often potential rather than actual. An electron does not have a definite position until we ask it, "Where are you?" by performing a measurement. This suggests that the observer is not separate from the reality they are observing. We are not merely an audience watching the play of the universe, we are actors on the stage, and our interactions help shape the story. This leads to the unsettling concept that reality might be relational. The properties of a system may not be absolute truths, but rather values that only exist in relation to the observer or the measurement device. This dissolves the hard line between the subject use and the object the world. Quantum entanglement adds another layer of mystery to this new view of reality. It reveals that the universe is non-local. In classical physics, influences travel through space at a finite speed. For object A to affect object B, something must bridge the gap between them. Entanglement shows us that particles can share a deep, instant connection that transcends space. Two particles, separated by light years, can behave as a single entity. This suggests that at a fundamental level, the separation between objects might be an illusion, and the universe is far more interconnected than it appears to our eyes. Furthermore, quantum mechanics has redefined our concept of information. In the classical world, information is distinct from the physical medium. You can write a message on paper or type it into a computer, and the message is the same. In the quantum world, information is physical. It is tied to the state of the system in a way that cannot be perfectly copied, the no-cloning theorem. This has given rise to the idea that the universe itself might be fundamentally composed of information, that bits and qubits are the true building blocks of reality, and matter is just how that information manifests. The loss of strict determinism is perhaps the most significant psychological shift. For centuries, scientists and philosophers believed that if we could know the present with perfect precision, we could predict the future. Quantum mechanics says, no. There is a fundamental limit to our knowledge, a veil we cannot lift. The future is not a single, inevitable track, but a landscape of probabilities. This introduces a kind of freedom into the cosmos, suggesting that the universe is not a pre-recorded movie, but a live performance that is being improvised moment by moment. These insights have sparked endless debates and numerous interpretations. Does the wave function collapse, or does the universe split into many worlds? Is there a hidden order we cannot see, or is randomness the true nature of God? While we may not have the final answers, the lesson is clear. Our everyday experience is a poor guide to the true nature of reality. The solid, predictable world we see is an emergent property, a stable illusion built upon a foundation of quantum fuzziness. Quantum physics teaches us humility. It shows us that the universe is stranger, more fluid, and more wonderful than we ever dared to imagine. Chapter 10. Quantum theory in the real world. It is a common misconception that quantum theory is a subject reserved for dusty chalkboards and high-tech laboratories, disconnected from the rhythm of daily life. While its principles are indeed abstract, quantum mechanics is not just a collection of ideas, it is the silent engine driving the modern world. From the smartphone in your hand to the medical scanners in hospitals, and from the lasers scanning your groceries to the satellites guiding your car, quantum physics has moved out of the theoretical realm and into the very fabric of our society. Let us consider the semiconductor, the material that forms the backbone of the digital age. The silicon chips that power computers, phones, and the internet operate based on the quantum behavior of electrons. In these materials, electrons are not free to move anywhere. They occupy specific energy bands. The gap between these bands determines whether a material conducts electricity or blocks it. By manipulating these quantum properties, engineers create transistors, tiny switches that control the flow of information. A single modern processor contains billions of these quantum switches. Without understanding the quantum rules of the electron, the digital revolution would never have happened. Lasers are another direct application of quantum theory. The word laser itself stands for light amplification by stimulated emission of radiation. This process relies entirely on the fact that atoms have discrete, quantized energy levels. When an electron in an atom drops from a high energy level to a low one, it emits a photon of a very specific color. By coordinating these emissions, we create a beam of coherent light where all the light waves march in perfect step. This quantum light is used to cut metal, perform delicate eye surgery, transmit data across the internet through fiber optic cables, and even read barcodes at the checkout line. In the field of medicine, magnetic resonance imaging, MRI, is a life-saving technology built on quantum principles. An MRI machine uses a powerful magnetic field to align the spins of hydrogen nuclei in the water molecules of your body. Spin is a purely quantum property. When the machine pulses radio waves, these spins are disturbed, and as they return to their aligned state, they emit a signal that the computer translates into a detailed image. This allows doctors to see inside the human body with incredible clarity, all thanks to our understanding of nuclear quantum mechanics. Even the Global Positioning System, GPS, which we rely on to navigate the world, would fail without quantum physics. GPS satellites carry atomic clocks to keep time with extreme precision. These clocks measure time based on the frequency of radiation needed to make electrons in cesium or rubidium atoms jump between quantum energy levels. Because these energy levels are fundamental constants of nature, atomic clocks are incredibly stable. Without this quantum precision, GPS would drift by kilometers every day, rendering it useless for navigation. Looking to the future, we see the rise of quantum computing. While classical computers process bits that are either 0 or 1, quantum computers use qubits that can exist in a superposition of both states at once. This allows them to explore a vast number of potential solutions simultaneously. Although still in its infancy, this technology holds the promise of revolutionizing drug discovery, materials science, and cryptography, solving problems that would take today's supercomputers millions of years to crack. Quantum mechanics is also reshaping how we understand biology. The field of quantum biology is exploring how nature might have mastered quantum tricks long before humans did. There is evidence that birds use quantum entanglement in their eyes to sense the Earth's magnetic field for migration. Photosynthesis, the process by which plants turn sunlight into energy, appears to use quantum coherence to transport energy with near-perfect efficiency. It seems that life itself may be dancing to a quantum tune. From the vastness of the cosmos, where quantum fluctuations in the early universe seeded the galaxies we see today, to the microscopic transistors processing this very video, quantum theory is omnipresent. It is the most successful theory in the history of science, never once failing an experimental test. It has transformed our world from one of steam and gears to one of silicon and information. As we conclude this journey, remember that the strange rules of the quantum world, superposition, entanglement, uncertainty, are not distant curiosities. They are the invisible threads that weave the tapestry of your reality. They are in the light you see, the technology you use, and perhaps even the biological processes that keep you alive. If you are still awake, thank you for joining the Sleepy Scholar on this exploration of the quantum universe. We hope you have found a sense of wonder in the mystery and a sense of peace in the complexity. If sleep hasn't found you yet, feel free to drift along to another video. Until next time, stay curious and sweet dreams among the stars.